Hello viewers, today we will be summarizing the steps and methodology used for analysis of flange sections. Though I have drawn T section here, all the equations and steps that we are going to discuss are applicable to L section as well. Typically, in the problem of analysis of flange section, the data such as BF, D, BW and DF will be given. Similarly, the area of steel on tension side will be provided. You will be knowing grade of steel and grade of concrete. And the question that would be raised is, where is the position of neutral axis at failure and what is the moment of resistance of this section? Mind you, we are dealing with singly reinforced flange section. There can be three cases that can emerge. The first case is XU is less than DF. That means neutral axis at failure lies within the flange. For that case, I have drawn the stress diagram here. So as you can see, the entire compressive stress block lies within the flange. 0.87 Fy is the stress in steel provided. In this case, MUR is simply written by replacing B by BF as if it is a rectangular section. So the expression is 0.36 FCK BF into XU. This is the compressive force, ultimate compressive force, multiplied by D minus 0.42 XU. This is the lever arm. The logic behind this is, if the neutral axis is going to lie within the flange, then anyway we are going to neglect the contribution of concrete on tension side, that is below the neutral axis if it is sagging, and in that case it is immaterial if the section below neutral axis is rectangular or T-shaped. Therefore, we assume this to be rectangle of dimensions BF cross D, and we write down the expression for MUR. Now let us look at the second case. Before going to the second case, let us first have a look at the third case, where XU is greater than DF. Not only that, 3/7 XU is greater than DF. So up to 3/7 XU from extreme compression fiber, we know the value of stress is constant, and that is 0.446 FCK. So if 3/7 XU is greater than equal to DF, then we are going to have entire flanged stress to the value of stress equal to 0.446 FCK. In such case, we write down MUR corresponding to contribution from CU1 and CU2. So what is this CU1 and CU2? So in such case, we divide the entire cross section into two parts. The first part is rectangular one, which has dimensions BW cross XU. For that, the value of compressive force is 0.36 FCK BW into XU, and its lever arm is D minus 0.42 XU. This is the first contribution in MUR. The remaining area of flange produces compressive force equal to 0.446 FCK BF minus BW into DF. BF minus BW into DF is the area of remaining portion of flange over which compressive force is constant, that is 0.446 FCK, because 3/7 XU is greater than DF. This compressive force acts at the distance DF by 2 from extreme compression fiber. So lever arm is D minus DF by 2. So the expression for MUR becomes 0.36 FCK BW XU into D minus 0.42 XU plus 0.446 FCK BF minus BW into DF into D minus DF by 2. Now let us come to the second case, where XU is no doubt greater than DF, but 3/7 XU is less than DF. So in this case, we are going to have non-uniform distribution of stress over the flange. In such a case, first of all, we find out YF. which is given as 0.15 XU plus 0.65 DF. Of course, this should be less than DF. So we assume that the depth of the flange is YF instead of DF, over which I can safely assume 0.446 FCK to be constant. So therefore, in the expression for the third case, we just replace DF by YF and we get the expression for moment of resistance of a flange section where XU is greater than DF but 3/7 XU is less than DF. The expression thus reads 0.36 FCK BW into XU into bracket D minus 0.42 XU plus 0.446 FCK BF minus BW into YF into D minus YF by 2, where YF is equal to 0.15 XU plus 0.65 DF less than DF. It has to be less than DF. So this was the summary of expressions that we use to compute moment of resistance of a flange section depending upon in which of these three cases the section falls. Now let us look at the flow chart for analyzing a flange section for its moment of resistance. The flow chart is going to look something like this. We will be given FCK, FY, BF, BW, D, AST and DF. All these terms are written in their standard notations. The first step that we do is we calculate TU knowing the value of AST. So TU is equal to 0.87 FY AST. So when we calculate TU equal to 0.87 FY AST, the implicit assumption that we are making is the section is under reinforced and therefore at failure steel is reached to its yielding. Steel has reached to its yield stress. So mind you, we begin with assuming the section to be under reinforced and then we calculate TU. Once the TU is calculated, we assume XU is equal to DF. That means XU lies at the interface between the flange and the wave. By assuming this, then we calculate CU. So what is the expression for CU? If XU is at DF, then the expression for CU will be 0.36 FCK BF into XU, which is DF. So 0.36 FCK BF into DF is the expression for CU. Then we check if CU is less than or equal to TU. If CU is not less than or equal to TU, that means CU is greater than TU, indicates the area on compression side should be less and therefore neutral axis must lie within the flange. So therefore XU will be equal to DF. Then we compute XU by equating CU and TU. So we write the equation 0.36 FCK BF into XU is equal to 0.87 FY AST. We compute XU. We compute XUB as KUB into D, where XUB is the neutral axis location for balance section. Then we check, is XU less than XUB? Yes. Then it is under reinforced section and then we compute MUR. So how do we compute MUR? We compute MUR for the case where XU is less than D. If no, that means if XU is greater than XUB, that means the section is over reinforced section. In such a case, we calculate moment of resistance of balance section and we report that as moment of resistance of the section. Now let us look at the other branch of this flowchart of this question. Is CU less than or equal to? The other possibility is no, yes, that means CU is less than TU. Therefore, we require more area on compression side. Therefore, we assume XU greater than DF and we assume 3/7 XU is equal to DF. So when 3/7 XU is equal to DF, that means the entire flange is going to be subjected to the stress of 0.446 FCK. Then we compute CU. We check this CU with TU. We ask ourselves a question, is this CU greater than TU? If no, that means we require CU to be even more. That means the neutral axis will venture into the web. and that means 3 by 7 XU is greater than DF. Once 3 by 7 XU is greater than DF is confirmed, we use the corresponding expressions to compute XU. We compute XUB. We check if XU is less than XUB. If yes, we compute MUR considering the case 3 by 7 XU is greater than DF. If no, then we say that MUR is equal to moment of resistance of balance section. Now at this location, we have established that XU is greater than DF, but we are checking if 3 by 7 XU is greater than DF or less than DF. So here if CU turns out to be less than TU, that means we require lesser area on compression side, indicating 3 by 7 XU is less than DF. So we compute YF. Using the expression for YF, by equating CU and TU, we compute XU. We compute XUB. We check if XU is less than or equal to XUB. If yes, then it is under reinforced section or at the most balanced section. Then we compute moment of resistance of a section using the case 3 by 7 XU less than DF. If no, then the section is over reinforced section. In such case, we prescribe MUR equal to moment of resistance of a balanced section. So I think we have covered the entire methodology of analyzing a flange section. With this, we will stop for today. Thank you.